thank you for your attention, even at this late time, the longest session. Mr. Tobias Hammer is associated. Mr. Tobias Hammer is associated to Professor Volk from the Technical University in Munich. All other authors are correlated to the Institute of Forming Technology and Gleitweit Construction. What I present you is the application of an advanced damage model to the process of shear cutting, and conclude with some analysis of the simulation. And shear cutting, we have a die which is held in position. The plane folder clamps the sheet and the punch is moving downward. This process involves really high strains here in the processing zone. And on the right hand side you see typical cutting surface quality. You see rollover, burnish and fracture. And appliers of this technology usually want large sections of burnish and avoid the fracture. So what we try with our simulation is a precise prediction of the forces placement curve and a good prediction of the cutting surface quality. How will we do this? How will we manage to get a simulation predicting experiments? I will present you the constitutive model that I've used, the way I've identified the parameters, the setups for the experiments of shear cutting and simulation of shear cutting, and at the end I will present the results, and I'm looking forward for the discussion with you. The constitutive model, it's another topic, plasticity, which is fully coupled to the damage model. I've seen most people here at the conference and other researchers as well prefer Gersensberger-Niedelmann. We have chosen a Lemaitre type damage model, where the effective stress is, an effective stress. So we don't have just a reduction in plasticity, we also have a reduction in elasticity. Most times seen as a disadvantage, and this time an advantage is the damage evolution, or the material parameters here highlighted in red, which are not correlated to physics. In GTN usually the parameters are correlated to the microstructure, and everyone is happy to find these things. But in shear damage, or in processes with low or even negative triaxiality, the damage is not due to void volume growth or nucleation. So here we have other mechanisms, and we can at the first stage be glad to have no physics here but a black box. What we've used is an enhancement of this model suggested by Pires and Soyersna, which considers the influence of compressive stresses and is implemented at our institute. What you see here is Y, the driving force for the damage evolution here. The sharp brackets are the Macaulay brackets. If the value inside the Macaulay brackets is positive, nothing will happen. That's our ordinary brackets. But if the value inside the brackets is negative, the brackets will return 0. So if the parameter h is equal to 1, we have ordinary Lemaitre model. If the parameter h is 0, no negative stresses will be considered in the damage evolution. Typical value for h is 0.2. The test we have done for identification is standard tensor test for the elastic regime and anisotropy. Notch tensile test shown here for the anisotropy. For flow curve, we have used a torsion test with a double bridge developed at our institute. We have also done some high-speed testing for checking influence of strain rate dependency. We haven't found that much influence, so we have neglected strain rate dependency. And for the identification of the prone damage evolution parameters, we have also used a tensile test with inverse identification. I will show you on the next slide. On the bottom line, the elastoplastic parameters are given. And on the right-hand side, you see the flow curve, which for the tensile test and for the torsion test. And you see torsion test can reach much higher strains than the usual tensile test. Yeah, how have we identified the damage parameters? We have used the notch tensile test with an initial guess of the damage parameters, simulated the notch tensile test in 3D, used of course some anisotropy planes. This is a valid approach because, as you can see here, and what I have not pictured here, the crack is perpendicular to all three directions. That's different to a standard tensile test. In standard tensile test, you usually have fracture in a 45-degree line, and you can't use symmetry lines if you want to identify damage or fracture. But with the notch tensile test, this was possible. Then we did repeated simulations with an optimization algorithm, and usually after 12 iterations, we got convergence and had found our parameter set. The experiments our colleagues in Munich did, the tool for that are shown here. We had a punch width of 50 millimeters here. So this process is a process with an open cut, contrary to punching or piercing with a closed cut line. The simulation setup was built in Abacus explicit. The contact between punch and sheet was done by node-to-surface contact. Of course, we had to use frequent use of ALE, arbitrary Lagrange Euler approach. The element size here in the region of processing was set to 0.02 millimeters and held to nearly constant during even ALE. Process parameters are shown above. So what can we see here? It's a validation. In red the experiment, in blue the simulation. I think the match is quite good. Below the evaluation of the surface quality. If you look at, on B is the experiment, on C is the simulation. If you look at the simulation, it's hard to say whether it's burnish or fracture. So I decided to use the triaxiality for identification if we have here burnish or fracture. If you know that shear loads usually have a triaxiality of about 0, and uniaxial tension has a triaxiality of roughly 0.33, and assume that fracture occurs under tensile load, you can say if tensile loads become dominant in this region, fracture occurs. So with this criteria, I found that burnish ends and fracture begins at this place. The burnish was made quite good. Some improvement are needed at the rollover and fracture. Now I want to analyze the simulation. What we have found is that shear cutting with the open cut has high influence of shear. That's not very astonishing, but it's astonishing to compare to the closed cut. You all know the triaxiality. Green is shear, uniaxial tension, yellow should be uniaxial tension, and so on. and nearly all of the process time we have shear dominance. Compared to the close cut, we have much more compression stress states, and the continuous shear band only exists for a short time during the complete process. So what can we say? We have found excellent prediction of the punch burst with the enhanced Lemaitre model. We have achieved good prediction of the cutting surface with the enhanced Lemaitre model due to the consideration of compressive stress weights. I've shown you an efficient parameter identification for the Lemaitre model, and we have found also that there are significant differences in the physics between shear cutting with an open and a closed cut. Thank you for your attention.